Hello, everyone. I'm Fengyang Lin from Columbia University. Today, I want to introduce our work on a sample size extractor for RCT reports. To begin with, I want to introduce some basic information about randomized control trial and sample size. Randomized control trials, also referred as RCTs, provides reliable medical evidence and have substantial impact on decision-making for patient care. Nowadays, information extraction systems has been developed to automatically extract structured and key information from free text medical literature. And some techniques has also been developed to extract the pico elements. So pico elements here is patient or population, intervention, comparison, and outcome. Among all these elements, sample size is one of the key information that could be extracted from P elements in RCT reports. So why do we care about sample size? Sample size is the indicator of the power, reliability, and efficacy of a RCT study. It impacts the statistical significance of comparisons. For example, a small sample size will make a trial less representative, and therefore it would decrease the efficacy of this outcome. Currently, there are two main ways to report sample size information. The first one is to report it indirectly from P elements text snippets. In this case, the size, the number are usually mixed with the words. So you still need to extract that number out. And the second way to do it is to identify any potential numbers or the sizes among all numbers. And this is also how trial streamer, the state-of-the-art method, are doing right now. However, we still need to address the issues that in extracting sample size, or say extracting a total sample size. So the first difficulty is that we need to distinguish whether the integer is a sample size or not. Given the text snippet here, let's say 30 women and along with other information, the extractor need to distinguish, first it need to identify the numbers and then need to distinguish whether the number is a sample size or is age, or does it represent any other demographic statistics. The second issue is it's hard to distinguish between the total sample size and group size. And nowadays, a lot of RCT studies, they will provide multiple population elements, and they will also provide multiple statistics for sample size. So additional checks and classification are usually needed. And it is also very important to know whether the sample size is a total one or a group one. For our study, we focus on total sample size. We think it a good place to start with, and we think total sample size is very representative. In order to design our extractor, we used two data sets. The first data set is from PubMed. So we directly downloaded 400 RCT abstracts from PubMed and divided them into two sets. The first one is COVID set. It contains 300 abstracts of COVID-19 RCT studies. And the second one is a more generalized one, general set. So it has 100 abstracts of RCT studies without any selection filters. Another data set we are using is EBM NLP. It is a public data set with annotated pico elements from 5,000 clinical RCT studies. We use this data set for pre-training. We also provide an example here for their annotated elements. As you can see now, it is annotated elements with a P tag and also a sample size tag. So it tells you whether the snippet contains information about sample size. However, as you can see here, the sample size is still mixed with the word participants. So you still need to extract this number out. And getting back to our own annotation, we identified and annotated any sample size related entities. And typically we divide our sample size entities into 4 categories. The first 2 are total sample size and group or arm size. Note that for each abstract, there is at most 1 true total sample size. So if there are also other reasonable number, we will label them as possible total sample size or possible group or arm size to distinguish them with the true one, because we want to focus on 1 total sample size, and we want to distinguish the sample size among total or group. Here is also a screenshot of our annotation interface. So with our annotation, we were able to create the gold standard for model chaining. The workflow for our extractor can be divided into 3 steps. After we input the RCT abstracts, we first pre-process them, and then we perform feature encoding with the design rules and embeddings. And then we train our multi-layer perceptron, or say the MLP models. Note that here we provide 2 options for the initialized weights for models, the randomized weights or the weights from pre-training on the EBM NLP corpus, as I mentioned before. In detail, for pre-processing, we first perform text normalization, that is to converting all numeric words to numbers. Then we perform tokenization and POS tagging. We also want to include information about the surrounding text. So we collected words and POS tags for tokens adjacent to the integers. Basically, we collect 2 words to the left of the integer and 2 words to the right of integers, and also their POS tags. Then we perform word embedding with word2vec for the words that we collected before. Afterwards, we perform feature encoding. Here we design several indicators of keywords to see whether certain keywords appear before, after, or nearby the integer. So the first indicator is about keywords that are obviously related to sample size, like patients and participants. The second indicator is about keywords for randomization population, like randomized and enrolled. And the third indicators is for keywords about analyzed population, like assessments and analyze. We split these indicators because we want to focus on total sample size that are most related to in the final analyze. And another important task is to distinguish group size from the overall sample size when they're both provided in abstracts. So here we also include numeric characteristics of total sample size, like whether this number is the biggest number in the abstracts, or is it the sum of any 2 other numbers. We also check percentile of the number and also check whether this number could potentially be a year. With features encoded for every integer in the abstracts, we could then move to train the model and get the results. Note that we also set a threshold for reporting total sample size, because we don't want to report any sample size that we're really not confident about. So here for an abstract, if the highest likelihood for all the integer is lower than 0.2, then no total sample size will be reported for this abstract. For evaluation, we perform cross-validation, and we use precision, record accuracy, and F1 for the metrics. We also conducted analysis on 2 levels, exact match and loose match. For exact match, the extraction is considered successful only when the extracted values is the same as the one in gold standards. For loose match, if the predicted, or say the extracted sample size is within the 10% tolerance percentage of the true sample size, we'll consider the extraction a success. Then we provided some examples of outputs extracted by trial streamer in our sample size extractor. Here, as you could see in the blue box, for a given abstract, the annotated true total sample size is 240, and the extracted size by trial streamer is 37 with a confidence of 0.99. And the reported total sample size by our sample size extractor is 240, which is the same as the true one, and our confidence is 0.51. More generally, we perform cross-validation as mentioned on both the COVID sets and the general sets. So for COVID sets and for the exact match level, the best average test F1 score is 0.73, and the best precision record is 0.67 and 0.8 respectively. Note that this was achieved by using our sample size structure and with pre-training weights from EBN and NLP corpus. And also we could compare among models that has pre-training or does not use the pre-training weights. So it shows that using the pre-training weights could improve the model performance. For general sets, we perform threefold cross-validation. And again, the best performance is achieved with our sample size extractor model with pre-training weights. So the best average test F1 score is 0.6, and the best precision record is 0.5 and 0.77 for exact match. And the case for loose match is quite similar. After that, we also we also perform some detailed analysis, and we also compare the model performance on COVID sets with specific annotated sample size entities. As shown in table 7, so our sample size extractor is better when several possible sample sizes are provided. And the table also indicates that possible total sample size is the most misleading number for the extractor. In conclusion, our contributions are threefolded. Firstly, we annotated 400 RCT abstracts from PubMed with sample size relevant information. It is a shareable resource. Secondly, we applied transfer learning methods, and we proved that it works for the sample size extraction task, and it works on our data sets. And lastly, our sample size extractor outperforms the state-of-the-art one because we could better distinguish total sample size, and because we train on a relatively small training data sets. Our sample size extractor can be applied to collect total sample size from any RCT abstracts. Our models could definitely be improved to report a more accurate total sample size. Several solutions might be designing a two-fold classifier to first identify whether a number is a sample size, and then to see whether that one is a total one. And another direction to work on is to extract group sizes or arm sizes, because they're also very representative information for RCT studies. Lastly, this work was supported by the National Library of Medicine grant. And if you have any questions, feel free to reach out to me. Thank you.